Welcome to Starship TV, Earth's natural warming toward a future hothouse climate. Introduction. Throughout geological history, Earth has shifted dramatically between cold ice ages and warm greenhouse states. While the planet is currently in an interglacial period known as the Holocene, it is still technically part of an ongoing ice age that began about 2.6 million years ago. New evidence suggests this warming trend may be accelerating due to a range of natural phenomena. These include increased volcanic activity, methane release, solar variability, electromagnetic shifts, and even cosmic events like asteroid impacts. This report explores the natural drivers of Earth's accelerated warming, the effect on ocean currents and jet streams, what life on such a planet could look like for future generations, what natural forces could eventually reverse this warming into a global cooling phase, how human influence compares to these overwhelming natural forces, the important role of carbon dioxide in plant life and the global ecosystem, and how migration and adaptation are necessary steps for the future of mankind. The natural warming cycle, from ice age to interglacial glacial background. The last ice age peaked around 20,000 years ago, with glaciers covering much of the northern hemisphere. Global sea levels were 394 feet 120 meters lower than today. Temperatures were 10.8 degrees Fahrenheit 6 degrees Celsius cooler on average compared to modern conditions. Holocene interglacial last 11,700 years, marked by warming due to Milankovitch cycles, variations in Earth's orbit and axial tilt. Sea levels rose and stabilized as glaciers retreated. Climate enabled agriculture and the rise of civilization. Despite the current warmth, we are still technically in an ice age, as permanent ice exists at both poles. However, natural forces may be pushing Earth toward a greenhouse period similar to past epochs. Natural drivers of accelerated warming. 1. Volcanism and tectonic degassing. Large volcanic provinces release billions of tons of carbon dioxide naturally over millennia. Undersea volcanism and mantle plumes may be under-detected contributors to warming. Historical example: Deccan traps approximately 66 million years ago caused intense greenhouse warming. Recent activity: ongoing eruptions from Iceland, Italy, Indonesia, and Kamchatka have released vast amounts of gases, aerosols, and ash into the atmosphere. Ash clouds reflect sunlight, cooling temporarily, but greenhouse gases contribute to long-term warming. These emissions can also affect jet streams and precipitation. 2. Methane clathrate destabilization. Methane frozen under ocean floors and permafrost could be released due to natural warming, known as the clathrate gun hypothesis. Sudden methane release. Rapid temperature spike. PETM 50/50. 6 million years ago, global temperatures rose 9 to 14.4 deg Fahrenheit 5 to 8 degrees C in less than 20,000 years. 3. Solar forcing and flares. The sun's output is not constant. Long solar cycles, example being Gleisberg, Suess, Hallstatt, influence Earth's energy balance. Solar flares and coronal mass ejections (CMEs) can heat the upper atmosphere and disrupt Earth's magnetic shielding. Increased solar radiation penetrates more efficiently when the magnetosphere weakens, may raise stratospheric temperatures and alter jet streams and ocean currents. Extreme example: the 1859 Carrington event, if repeated today, could disrupt energy systems and atmospheric chemistry. 4. Geomagnetic pole shift. Earth's magnetic poles are drifting at accelerating speeds. The North Pole is moving over 25 miles 40 kilometers per year. Geomagnetic reversals occur every 200,000 to 500,000 years. The last was approximately 780,000 years ago. During pole shifts, magnetic shielding weakens. More cosmic and solar radiation reaches Earth. Can cause atmospheric ionization, cloud changes, and warming. 5. Asteroids or comets melting. Polar ice impacts deliver immense thermal and kinetic energy. A comet or asteroid striking polar ice could rapidly melt ice, cause immediate sea level rise, release trapped methane and microbes. Example: Younger Dryas impact hypothesis approximately 12,800 years ago suggests a comet caused rapid cooling then warming. A 1-2 kilometers asteroid equal to energy greater than 1 million megatons TNT, enough to destabilize ice sheets in hours. Ocean jet stream disruption, a climate balancer at risk. Earth's oceanic jet streams, such as the thermohaline circulation and Atlantic meridional overturning circulation (AMOC), regulate climate globally. These currents transport heat and salt around the globe. How natural factors interfere. 1. Melting ice and freshwater influx. Glacial melt introduces freshwater into oceans, reducing salinity. This prevents dense water from sinking in the North Atlantic, weakening AMOC. 2. Volcanic activity. Volcanic ash can cool upper oceans and reduce sunlight penetration. Sulfate aerosols reflect solar radiation, shifting wind and rainfall patterns. 3. Solar and geomagnetic variability. A weakened magnetosphere allows more solar radiation, alters polar vortex and jet streams, which are coupled with ocean currents. 4. Methane bursts. Intensify warming, leading to more ice melt and salinity changes. 5. Cosmic impacts. A large asteroid or comet could displace ocean layers, or introduce vast amounts of fresh water, instantly disrupting currents. Current signs. AMOC is now possibly the weakest it's been in 1,000 years. Impacts include cooling in Europe, shifting monsoons, and North Atlantic storm changes. Early signs of an accelerated transition. Arctic permafrost is thawing rapidly. Greenland and Antarctic glaciers are retreating faster than expected. Oceans are warming faster than at any point in the last 10,000 years. Volcanic emissions from recent eruptions contribute to both cooling via ash and long-term warming via CO2. What a natural hothouse Earth might look like. Global temperature rise. Earth could warm 7.2, 14.4 degree Fahrenheit 48 degrees Celsius above pre-Holocene levels in a few thousand years or faster with amplifiers. Sea level rise. Total polar ice melt equal to sea level rise of up to 246 feet 75 meters. Coastal cities and nations would be submerged. Floodplains in Asia, US, Europe and Africa were lost. Biosphere shifts. Tropics may become too hot and humid, wet bulb greater than 95 degree Fahrenheit or 35 degrees Celsius. Rainforests dry out, savannas replace them. Oceans suffer mass marine die-offs. Adaptation and migration, life for future humanity. Poleward migration, habitable zones, shift to the Arctic and Antarctic circles. Northern Canada, Alaska, Greenland, Siberia, and ice-free Antarctica may become new temperate zones. Requires resilient infrastructure, floating or elevated settlements, agriculture and resources. New farmland emerges in formerly frozen areas. Greenland valleys and Siberia may support crops and livestock. Polar oceans replace tropical fisheries. Technological adaptation. Underground cities or climate-controlled domes. Ocean-based living platforms. Terraforming cold regions to support vegetation. What could cause a future global cooling? While warming is a current concern, Earth has repeatedly returned to cooler states due to various natural feedback loops. Several forces could halt or reverse the warming trend. 1. Major volcanic supereruptions. Massive eruptions like Yellowstone or Toba could inject vast quantities of sulfur dioxide into the stratosphere. Result: global dimming, crop failures, and years of cooling. Toba, approximately 74,000 years ago, may have caused a 6 degrees Celsius global temperature drop. 2. Reduced solar output, grand minima. The Sun periodically enters quiet phases such as the Maunder minimum, 1645 to 1715. Reduced sunspots and energy lead to cooler conditions. The Little Ice Age coincided with these solar slowdowns. 3. Ocean current collapse. If AMOC collapses entirely, it could halt heat transport to the northern hemisphere. Paradoxically, this could cause regional cooling even as global averages rise. 4. Increased cloud albedo. Volcanic aerosols or cosmic dust could enhance cloud formation, reflects solar radiation, contributing to global cooling. 5. Massive asteroid impact. An impact on land could generate huge dust clouds, blocking sunlight for months to years, similar to a nuclear winter scenario. 6. Methane sequestration. By microbial blooms, sudden growth of oceanic microbes could consume vast amounts of methane, reducing warming potential. Requires specific temperature and nutrient conditions. 7. Biosphere feedbacks. Forest expansion in northern latitudes increases carbon drawdown. Species evolution or extinction may reset the ecological balance. These cooling forces may act suddenly or gradually, reminding us that Earth's climate is a system of competing feedback loops. Human impact versus natural forces. Human activities such as fossil fuel combustion, deforestation, and industrial emissions contribute to climate change, but the scale of their impact must be considered in context with Earth's vast natural systems. Human contribution to warming, estimated to account for 10 to 25% of current observed warming trends, primarily through elevated CO2 and methane levels. Natural forces contribution account for 75 to 90% of long-term climate shifts, especially through solar cycles, volcanic activity, methane clathorates, and orbital changes. While human influence is significant and rapidly accelerating in the last 150 years, it remains dwarfed by the geological scale energy and matter fluxes from natural systems. However, human activity can act as a trigger or amplifier of natural processes. Example: releasing methane from thawing permafrost. The role of CO2 in plant life. Carbon dioxide, while often cited as a greenhouse gas, is essential for plant life. It serves as the primary carbon source in photosynthesis, enabling plants to grow, reproduce, and build biomass. Increasing atmospheric CO2 has shown measurable benefits to plant life. Enhanced plant growth. Many crops and wild plants grow faster and larger under higher CO2 concentrations, especially in controlled environments. Improved water efficiency. Plants often reduce water loss, transpiration under elevated CO2, increasing drought resistance. Greening effect. Satellite imagery over the last several decades shows increased greening in some arid and semi-arid regions. While this does not negate the broader risks of climate change, it highlights that carbon dioxide also plays a fundamental role in sustaining life on Earth. You're watching Starship TV. Like, comment, and subscribe for more content exploring Earth, space, and the future of humanity. Conclusion. Earth's long-term climate destiny. Earth has undergone dramatic shifts in climate long before humans appeared. From massive asteroid strikes to continent-sized volcanic eruptions and solar surges, natural processes have reshaped the planet multiple times. Today, a convergence of such natural amplifiers, volcanic degassing, solar variability, geomagnetic pole shifts, and cosmic impacts, may be accelerating Earth's path toward a naturally driven hothouse Earth. However, counterforces such as supervolcanoes, reduced solar output, and ocean current failures could just as easily trigger a return to Ice Age conditions. Understanding that these changes are part of Earth's dynamic system allows us to prepare for the future with realism, not fear. While human activity contributes to environmental change, adapting and migrating in response to much larger natural climate drivers is the realistic and necessary path for the survival of civilization. By understanding Earth's natural rhythms, we can plan intelligently, preserve biodiversity, and ensure humanity thrives in harmony with the planet's powerful and evolving climate systems. This is Starship